Is 1 to infinity of negative 1 to the k plus 1 times k plus 3 over k times k plus 1. In this particular problem, your AK is k plus 3 over k times k plus 1. We need to show that this is decreasing. The easiest way probably to show that this is decreasing is probably to take the derivative. To take this derivative, we would need to use the quotient rule. Let's multiply the denominator out. You get k squared plus k on the denominator. The derivative of a sub k, you take the bottom and square it. You take the bottom times the derivative of the top, which is just 1, minus the top, k plus 3, times the derivative of the bottom, which is 2k plus 1. And now lots of fun doing some algebra. K squared plus k times 1 is just k squared plus k, minus k plus 3 times 2k plus 1 will give us 2k squared, plus k plus 6k, which is plus 7k, plus 3. Over k squared plus k, the whole quantity squared. So that will equal, k squared plus k minus 2k squared minus 7k minus 3. All over k squared plus k, the whole quantity squared. Simplifying that, combining your like terms, this k squared and this negative k squared will make negative k squared. This k and this negative 7k makes negative 6k minus 3 over k squared plus k, the whole quantity squared. Now looking at this numerator, k squared is itself a positive value, but when you negate it, this is now negative. I'm taking a negative value. We also know that k is going from 1 to infinity, so the only possible values for k are positive. So negative k squared is now negative. Negative 6 times a positive number is negative, so this is even more negative. So ultimately, the numerator is completely negative, and the denominator is always positive because it's squared. So this, even if it weren't squared, k squared plus k would still be positive. But that's now obviously negative, which means this is decreasing. And now the easier thing to show is that this limit is 0. This is k plus 3 over k squared plus k. And again, I think we all know by now that when the degree of the numerator, when the degree of the numerator is lower than the degree of the denominator, this limit is 0. So yes, we now know from the alternating series test that this series converges. Next, we'll talk about a couple definitions. A series converges absolutely if the absolute value of the series converges. For example, the series from k equals 1 to infinity of negative 1 to the k plus 1 times k squared, 1 over k squared. So think about all this is saying to you. This is simply saying if I take the absolute value of negative 1 to the k plus 1 times 1 over k squared, the absolute value bars invalidate the negation. So this is really 1 over k squared. There is no more alternating. Since the sum of 1 over k squared, I should have had some here. Since this is a p series with p equaling 2, this series converges. Since the absolute value of the original series converges, it converges absolutely. On the other hand, the following series converges what's called conditionally. So if a series converges when there is no absolute value bars, but diverges when there are absolute value bars, it's said to converge conditionally. So for example, the series 1 over k, we looked at that previously 2 examples ago. The alternating series converges because it's decreasing and the limit of 1 over k is 0. So the alternating series converges. However, if you take the absolute value of that series, if we take the absolute value of this series, again, that nullifies the negative component of it, and you are now looking at just the series 1 over k, which is the harmonic series It's a p series with p equal to 1. So when you take the absolute value of that series, it diverges, but when you look at the original alternating series, it converges. That's called converging conditionally. We now have a theorem. This theorem states if the absolute value of a sub k converges, then the sum, there should be a sum here. If the sum of the absolute value of a sub k converges, then the original series also converges. In other words, this means absolute convergence oh my, I don't know what I just did, sorry. Absolute convergence implies convergence. Here's the proof. Suppose the sum of the absolute value of a sub k converges. So then the sum of a sub k without the absolute value bars is equivalent to, and this might be odd, but you'll see where we're going, the sum of a sub k is equivalent to adding on the absolute value of a sub k and then subtracting it off. The part that we're interested in here is right there. A sub k plus the absolute value of a sub k. Now, if a sub k is negative because it's an alternating series, the absolute value of that is positive. So this ends up being double. Or if one is negative and this one's positive, well, what I'm saying is if they're both positive, it's equivalent to 2 times the absolute value. If this one's positive because it's an absolute value and this one's negative, you get a 0. So that implies that this thing right here is between 0 and 2 times the absolute value of a sub k. So the sum of a sub k plus the absolute value of a sub k is less than or equal to the sum of 2 times a sub k. Now, because we know from the beginning, right here, that the sum of the absolute value of a sub k converges, that means that this too converges. Even though there's a multiplier of a 2 here, that doesn't matter. You can take the 2 out, that will still converge. If that converges, by the comparison test that we learned last time, we now know that this converges. But that is actually 2 series being added together. We know that this one's a convergent series. For 2 series to add together to still converge, they both have to converge. So this implies that a sub k also converges. Ultimately, All we're saying is that if a series converges absolutely, that implies the series converges.